Welcome back. Today we cover something called parametric equations. Note that a couple of things are happening. Project number 8 is collected today, so look at that date over there on your calendar to know exactly when that's due. Also required form 3 is due on class 34. I put it here because we also have a quiz next class, so make sure you're working on that as well. And we've got 2 more classes to cover and then our review day for test number 3. So let's start with the notes. Number 1, suppose we want to describe how an object is moving in a plane. The ordered pair xy could represent the object's position at time t. An equation in x and y can be used to describe the path the object is taking, but it doesn't give any information about when the object is at a given point. For example, suppose an object is following the path y equals x squared. So we've got this object following the path y equals x squared. And essentially we, maybe like look at this as like a track in the mud. And so you have evidence that somebody was here and here and here and here and here, but we don't have any idea were they going this way, were they going this way, were they walking slowly here and then speeding up and then walking slowly on the other side. All we have is this finished like mud track. So it tells you where they were, but really doesn't tell you anything about when they were there or how quickly they moved or their acceleration or any of that jazz. So that's basically what this says here. We know the object is at some point on this parabola at every moment in time, but we have no idea where the object is at any moment in time. 3, now suppose I tell you the object's position is given by, and now here's a piecewise function because it has 2 different rules, but it's kind of different. At least it looks like a piecewise function, but it's really weird. I'm telling you what x is, and I'm telling you what y is, both in terms of this other letter, t. So x equals t and y equals t squared. So where is the object after 1 second? Well, just plug 1 in for both of those t's, and we find out that x is equal to 1, and then y is equal to 1 squared, which is also 1. So at t equals 1 second, the object is right here at the point 1, 1. So I'm just going to put t equals 1 second. And then if we go to t equals 2 seconds, plug in 2 for both of the t's. So x is equal to t, which is 2. Y is equal to t squared, which is 2 squared or 4. So that's the point 2 comma 4. So right here, the object is at the point 2, 4 at t equals 2 seconds. Then at t equals 3 seconds, x is t, so that's 3, and y is t squared, which is 3 squared or 9. So the point 39 is up here at t equals 3. And I didn't ask for it, but let's just do t equals 0. When you plug 0 in for both of those t's, you get the point 0 for x and 0 for y, which is right down here at t equals 0. So we know that at t equals 0, the object is here. 1 second later, it's here. So it traveled this part of the path in the first second. Then in the next second, between t equals 1 and t equals 2, it traveled a lot further. But it still just took a second like before. So it went a lot faster here than it did here. And then between 2 and 3 seconds, it traveled this much longer distance. So the object apparently is really speeding up as it gets from one point to the next. And so it's the same exact set of points, whether I call it y equals x squared or this new thing, but we get a lot more information using this new thing. You know exactly where the object is at any moment in time. You can think about velocity. You can think about acceleration. Put an arrow on the parabola to indicate direction of travel. Well, apparently this thing is traveling this way. Put a few arrows. We didn't do any negative values of time, but we would have ended up seeing that the direction of travel was consistent, left to right. 4, the variable t is called the parameter, and the equations x equals t, y equals t squared are called parametric equations. 5, consider the parametric equations x equals t plus 1, y equals t over 2 for 0 less than or equal to t, less than or equal to 5. I'd like to see what motion this represents. First thing we'll do is plot points corresponding to the integer values of t between 0 and 5. So let's make a table. So we've got t, we've got x, we've got y. And the values of t that we're going to have will be the integers from 0 to 5. 0, 1, 2, 3, 4, and 5. And then we're going to plug in these guys into the x and into the y. So let's plug them into the x first. So apparently x is always 1 more than t plus 1. So if you plug 0 in for t, you get 0 plus 1. Plug 1 in for t, 1 plus 1 is 2, 3, 4, 5, and 6. And then in red here, we'll plug those same t values into this equation, which says that y is always half of t. So half of 0 is 0. Half of 1 is a half, or 0.5. Half of 2 is 1. Half of 3 is 1.5. Half of 4 is 2. Half of 5 is 2.5. And now we're going to temporarily ignore this guy and just plot the points that we found. 1, 0.5. That's a point. So 1, 0.5 is here. 2, no, I misread what I wrote. It really says 1, 0. 1, 0 is here. 2, and then 0.5 is here. 3, 1. 4, 1.5. 5, 2. And then 6, 2.5. And lo and behold, we get something that appears to be a line. So we will boldly just try to generalize this guy and say, well, that's what it looks like. And we're heading in that direction. Although I guess technically if this one is restricted to being between 0 and 5, then it doesn't get past either of these dots here. Okay, so that's fine, but we do have definitely that direction of travel. And B says, now we'll eliminate the parameter by solving one equation for t and substituting into the other. Okay, makes no difference which equation you solve for t. I'll solve the first equation for t, and I'll get t is equal to x minus 1, and then I'm going to plug that t into the other equation. Y is equal to t over 2, but instead of t, x minus 1. And so y is equal to x minus 1 over 2, which if you prefer, y is equal to 1/2 x minus 1/2. That's just kind of distributing that 2 in the bottom. And lo and behold, oh yeah, it's a line. Y equals mx plus b form. So the slope is a half. Does that make sense? Yeah, it looks like the slope of this guy is a half. The y-intercept is negative a half. If we had drawn this a little bit further, we would have found the y-intercept at negative a half. So apparently, this stuff right here is just the familiar line, y equals 1/2 x minus a half, but with more information given. Part C, we'll graph the parametric equations on our calculator. So let's go to the calculator. The first thing we're going to do is go into mode. Now, if you come down here to the fourth line, you'll see normally we're in function mode. Earlier this semester, just a few classes ago, we looked at polar mode. Today, we look at PAR, parametric mode. So hit enter right there. Looks the same here, but if we're trying to graph this thing, so if we go into y equals, we're going to see something completely different. X sub 1 t equals y sub 1 t equals x2, y2, x3, y3. Okay, so apparently we want to type in this, x equals t plus 1. So I guess we're typing in t plus 1 right there in the top line. So how do we get a t? Well, you could use this green t right here. But if you look at our favorite variable button, it says x, t, theta, and n. Well, let's just try hitting that button. Oh, look, it's a t. So depending on what mode you're in, you're going to get the different standard letter. So t plus 1 is good. And then y is equal to t over 2, t divided by 2. Let's go into the window. Instead of going 0 to 2 pi, let's go 0 to 5. Again, the window is different now. It has a t min and a t max. So let's go 0 to 5. The step size just tells you how often it's going to put a dot. The smaller the step size, the more accurate the graph, but the slower the graph will go. 0.1 is probably fine. X min and X min, X max, let's try -6 to 6, just so it really looks like the one that we've got here. And then -6 to 6 on this one too. So if you've got your graph set up like that, your window set up like that, hit graph, and it should look like this. Now before we hit graph, I'm going to say more than just saying it looks like this. I'm going to say this graph is going to start right here, which is where our first point was, and it's going to move up this way at an even speed, which is different than our parabola, because the parabola was going slow and then faster and faster. So we're going to get something which is moving at an even speed, and it's going to stop right there at the point 6, 2.5, which will be kind of weird because normally on the graph, on the calculator, the lines go forever, at least to the edge of the window, but this one's going to stop. So it's going to start right there, even speed, and it stops right there at 6, 2.5. If you really want to make sure that you see that it stops, change your X max to 10, and you'll see indeed that it stops at 6. Okay, so on the next page, so next class we'll see much more on applications of all this, including the return of the bicycle wheel from that project. We'll do a few of these together and then you'll work through the rest as the activity. I actually think I'm just going to make a video for all of them, but you're going to maybe watch me do the first one if you want, but do as many of these as you can on your own before you look for the video to help you get through any difficulties. For each set of parametric equations below, plot enough points to get a sense of the curve that describes the motion. Some points may be off the graph paper just to estimate where they should be in these cases. Eliminate the parameter, draw a smooth curve that represents the motion, make an observation about the motion. That could be something like it's traveling at a constant speed, or it's moving slow and then fast and then slow. Check the graph on the calculator if you are so inclined. Okay, so part A, x equals t, y equals t, for 0 less than or equal to t less than or equal to 3. So first thing we'll do is plot a few points. So we'll make our table here just like we did before, t and x and y. And here we're going between 0 and 3, so how about we just pick the integers. And it says x is equal to t, so apparently we copy the t values here, but y is also equal to t, so we'll copy those values there. Then we'll plot the points ignoring the t column, or the t row. So 0, 0, 1, 1, 2, 2, 3, 3. So it feels like we've got the behavior here. It looks like another line, so we'll go ahead and draw our line here. I'm also going to put arrows. So then it says eliminate the parameter. So this one is going to, there's not a whole heck of a lot to do here, but part 2, you solve one variable for t. It's already done. The first equation is solved for t. Substitute that into the other equation. So it said y equals t, but instead of t, we can put x, because that's what t is. So apparently this is the line y equals x. Well, okay, that's not surprising at all. It looks just like the line y equals x. And then draw a smooth curve that represents the motion. We've done that already. Make an observation about the motion. So is this thing slow then fast, or fast then slow, or constant speed? So it feels like this one is a constant speed. Those points were equally spaced apart, which is different from the parabola that we saw at the start. And then check the graph on the calculator if you are so inclined. I am not, but maybe you should be. Part B, x equals t cubed, y equals t cubed, again between 0 and 3. All right, so I'm going to do these ones very quickly. Again, I'd encourage you to do as much as you can on your own before relying on the video. But like I said, I'm going to zip through these because it's largely the same thing, although some of the eliminating the parameter gets tougher on the later examples. Yeah, let's just go through these here. So same idea as before, 0, 1, 2, 3. Plug those into the x, which is t cubed, 0 cubed, 1 cubed, 2 cubed, 3 cubed. Y is also t cubed, so these are the same numbers. And again, ignoring that and plotting the points, 0, 0, 1, 1, 8, 8, 27, 27, 0, 0, 1, 1. All right, 8, 8 is already off the graph, so it's up there maybe. And then 27, 27, I'm not even going to try. So I guess what we see here is, well, it's the same line. It goes all the way up to 27, 27, but the movement here, the motion here is quite different. In 1 second, we travel this space, but then in the next second, we travel a much bigger space. And then 1 second later, we're even further out. So I guess I'm ready to answer part 4 here already, is that we're moving on a line, but we're moving faster and faster. Okay, so one thing I didn't do yet is eliminate the parameters. So let's try that here. So solve the first equation for t. T is the cube root of x. Plug that into the second equation. Instead of t cubed, instead of t, we're going to put cube root of x. But the cube root of x cubed is just x. So again, this is the equation y equals x. And we already made our observation. Checking the graph on the calculator, I actually am inclined on this one because I just want to show you how different the motion is and how you can really see this thing speeding up. So we're going to type in t cubed here and then t cubed here. And I'm going to fiddle with the window a little bit here. I want to go, instead of just 0 to, yeah, it's actually 0 to 3 is what I want to do. And 0.1 is fine. We can tweak that. Let's go like, I don't know, -2 up to 30, because I know we have to get to at least 27. -2 up to 30. Okay, so what I want to see is this guy starting at the origin, going slow, and then speeding up, and then shooting off to the top right. Okay, it kind of happened quick. I guess I saw it, but I really knew what I was looking for. So what if you don't? Well, if you want to slow it down, then just make a smaller t-step. So it should be slow and then faster, faster, faster. So this one is really slow. You can hardly see anything happening. There it is gradually, and then speeding up, speeding up, speeding up, and moving along at a good clip at the end. Okay, part C, root t, between 0 and 3. Same idea. Square root of 0, square root of 1, square root of 2 is about 1.4, square root of 3 is about 1.7. And these guys are exactly the same. So we'll get these points here, 0, 0, 1, 1, 1.4, 1.4, 1.7, 1.7. Let's try that 1.4 again. 1.4, 1.4 is there. 1.7, 1.7 is very nearby. So we get the same line, but now actually in the first second we cover this distance, and in the second second hardly anything, and in the third second we barely move at all. So our observation about the motion here is that it's again on a line, but slower and slower. Eliminating the parameter, let's see here, so this is part 2. So solve the first equation for t, and we get x squared. Plug that into the other equation. Y is the square root of t. T is really x squared. And the square root of x squared is x. Okay, it's not really. It's really the absolute value of x. Not worried about that detail at this moment. So it's the same line, but now we get just a small piece of it, and it's moving slower and slower. I'm not inclined to graph that on the calculator, but you probably should be. D, finally something different. So I'm not, well, okay, let's do this one. So we'll make our table. T plus 1 is the x, doubling the t to get the y. And we'll plot these points. And then 4, 8 is somewhere just off the graph. So this looks like another line. And moving that way, and this one, I guess I can say that it looks like these points are equally spaced. So looks like we're going on that line at a constant velocity. So here's where the algebra ramps up just a little bit. So solve the first equation for t, x minus 1. Plug that into the second equation, 2 times t, but t is really x minus 1. So 2x minus 2 is the, y equals 2x minus 2 is the equation of that line. Does it make sense? Slope equals 2, that's good. Y-intercept, if we had continued, would have been at -2. Part E is quite similar, but here the domain, that is the t values, is extended. Instead of just stopping it at 0, I'm allowing it to go back here to -3. So we don't need to do everything all over again, but we just kind of need to extend our table a little bit. In fact, I'm just going to be really lazy here, and I'm just going to plug in the -3 into both. So when you plug -3 in for the x, -3 plus 1 is -2. 2 times t, or 2 times -3 is -6. So the point -2, -6, -2, -6 is down here. This is the one for t equals -3. And apparently we just get more of the line. Still going the same direction. Okay, where f has t squareds. All right, so that feels like a parabola. So we're done with these silly lines. Let's see here. So we'll make our chart as usual. Okay, so t squared plus 1, 0 squared plus 1, 1 squared plus 1, 2 squared plus 1, and then 3 squared plus 1, and then 2t squared. And then we'll plot the points, 1, 0, 2, 2. What's next here? 5, 8, so that's off the screen. Let's move this up a little bit. So 5, and then ballpark for 8, 6, 7, 8, maybe there. And then 18, 10, I'm not going to try. So do we have a parabola here? Well, actually, kind of looks like a line again. In fact, I think those 2 points are the same as the ones that we had above, aren't they? 1, 0, and 2, 2. Okay, and I paused the video there because I was nervous because I saw the first 2 points were the same, but then the second point, 5, 8, is different than the point that I got up here, which was 4, 8. And the reason they're different is because I'm an idiot and I don't know how to double the number 3. So let's fix that. So 6 there. So that should have been the 0.46. So then let's fix my error from before. So 4.6 is right there. So just didn't quite get off the graph, and that's okay. So let's see. It feels like it's just the same line again. I mean, it's traversed a little bit differently, but somehow those t squareds didn't give me the parabola I was expecting. But we can talk about velocity. In the first second, we covered that distance. In the second, much larger distance. So apparently we're speeding up here. So part 4 in this one is we're following a line, but not at a linear velocity. Here we're speeding up. Okay, eliminating the parameter. Let's do the algebra here. Solve the first equation for t. This will take a couple of steps. In fact, I'll give myself a little more room up here. So x minus 1 is t squared, and then square root of that guy to solve for t. X minus 1 square root, and then we're going to plug that into the other equation. Y equals 2 times t squared, and instead of t, root x minus 1. And then 2, and then root x minus 1 squared is just x minus 1. Okay, it's really absolute value, but again, I'm not worried about that detail. So we get y equals 2x minus 2, exactly the same line, but just speeding up. Okay, and if you're on the ball, you actually can save a little bit of work in some problems, like this one. If we had just stopped right here, instead of solving all the way for t, had just stopped at solving for t squared, then we could have just immediately plugged this guy in for the t squared. We didn't need to get all the way down to t. We could have just plugged right in and gotten 2 times this guy, which is really x minus 1. And that would have skipped us ahead to here. Okay, a trig one for the first time. X is cosine t, y is sine of t, 0 to 2 pi. For this one, plot the points corresponding to 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, we can do that. Okay, so let's do the cosine part first. So cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is minus 1, back to 0, back up to 1. Sine of 0 is 0, and it's on its way up to 1 at pi over 2, back to 0, down to minus 1, back to 0. And then we'll plot these points, 1, 0, 0, 1, minus 1, 0, 0, minus 1, and then right back to 1, 0. And I mean, it could be a square, I guess, but just kind of feels like we're curving around here. And maybe we've got the unit circle traced out, starting right there at t equals 0. Okay, let's see. So then if we solve or eliminate the parameter, let's see what happens here. So 2 says we're going to solve for t. Okay, solving for t is not the best idea. It's going to give you inverse cosine of x, which you can then plug into the other equation. Sine of t is really sine of inverse cosine of x. That is not the equation of any circle that I've ever seen. So when I said solve for t, that was really just a suggestion, but you don't have to do it every time. Really what you want to do is eliminate the t, eliminate that parameter. So I'm going to do something that might appear funny in the beginning. I'm going to square both sides of both equations. So x squared is definitely cosine squared, and y squared is definitely sine squared. And the next thing I'm going to do is add the two equations, and now you might see where we're going here. So the left-hand side is x squared plus y squared. The right-hand side is cosine squared t plus sine squared of t. But what is cosine squared plus sine squared no matter what t is? Well, that's one of our big identities. It's 1. Lo and behold, x squared plus y squared is the familiar equation of a circle centered at the origin, radius of 1. So I guess we're right here with the motion here. It's a circle. And we're traveling which way on the circle? Counterclockwise on the unit circle, starting at the point 1, 0. Okay, part H, same problem, and says you don't need to do everything all over again, but just add to the previous sketch. The only difference here is that instead of stopping at 2 pi, we're going to allow us to go around to 4 pi. Well, you can imagine that we're going to get exactly these same 4 points just copied over again. And so let's see, that was point 1, 2, 3, and 4. And the next points would be here, 5, 6, 7, and 8. So there's nothing really to draw. I guess I'll just describe that here we're just tracing the circle twice. Right, next page. X is cosine of 2t and y is sine of 2t. Okay, let's give this a shot. Okay, so we've got t and x and y. Okay, so 0 seems like a good starting point here. And then we'll do the same points. I'm going to leave a little bit of space actually, but I'll put pi over 2 here, and then pi, 3 pi over 2, and 2 pi. So how do I know that I should leave some space? Well, I don't know. I've done this problem before. So you wouldn't know unless you'd done it before, but we'll see why we're leaving some space. So let's plug in. So we're doing cosine of 2t. So cosine of 2 zeros, cosine of 0 is just 1. Next one, things get funny. Cosine of 2 times pi over 2. That's really just cosine of pi. Cosine of pi is minus 1. And then we plug pi in for t, and we're doing cosine of 2 pi, which is back at 1. And then cosine of 2 times 3 pi over 2 is really cosine of 3 pi, which is back at minus 1. And then I like patterns, so I'm just going to assume that's a 1 down there. Let's see what happens. So we didn't get any of the zeros, which we're kind of expecting. Well, let's see what happens with the sine. So sine of 2t, sine of 2 times 0 is 0. Sine of 2 times pi over 2 is really the sine of pi, which is 0. Sine of 2 times pi, 0. Sine of 2 times 3 pi over 2 is really the sine of 3 pi, which is 0. And then patterns, it's a 0. Okay, so let's go ahead and plot these points. 1, 0 is here. Negative 1, 0 is here. And then we just get more copies of those 2 points. So apparently we're just kind of bouncing back and forth on this line. So I guess we're just kind of zipping back and forth somehow. Okay, so I left a blank space there. I left blanks between these points. So let's fill in. I'm going to put pi over 4 right here. And I'm going to put 3 pi over 4 right here. That's probably good enough. You can fill in the others later if you want to. So let's plug in pi over 4 into the cosine. So we're doing cosine of 2 times pi over 4, which is really cosine of pi over 2. And cosine of pi over 2 is 0. That's the 0 that we were missing, right? Normally with cosine, you'd have 1, and then 0, and then minus 1, and then 0. And in fact, if you check, you will get a 0 right over there. So I'm going to go ahead and fill in 0 there, 0 there, 0s in the other blanks. Let's see what's going on with sine. So if we do sine of 2t, 2 times pi over 4, this is really sine of pi over 2. And that's up at the top, so that's a 1. 0 there, 1 there. Next one is back at 0. Next one is at minus 1, and then it repeats. So let's plot these new points in purple. So we got the point 0, 1. That's up here. I was way wrong when I said we were just bouncing back and forth between these points because we still get up to the top. And then the next point is 0, minus 1. It's down here. So in fact, what you're going to see is that we're still tracing out a circle, starting at this point, hitting up at the top, going down to the bottom, and then getting back to the first point. And we finish our first complete cycle of that circle right there when we get back to pi. So I guess we can write that here. So that's at t equals 0, and then again at t equals pi, and then again at t equals 2 pi. So apparently this is really two copies of that circle. So we're doing a counterclockwise circle twice around, and then starting at the point 1, 0. Okay, so I think that's fine. I'm not going to do the eliminating the parameter, but I'll let you give that one a shot. It's quite similar to the one we did before. Okay, x equals 5 cosine t, y equals 2 sine of t, 0 to 2 pi. So we'll start with our standard table. Okay, so we're doing 5 cosine of 0. So cosine of 0 is 1, so this one is 5 times 1, or 5. Cosine of pi over 2 is 0, so multiplying that by 5 doesn't change anything. The next one's normally at -1, but it's multiplied by 5. Next one is still 0, and the last one is back up at 5. And then plug 0 in, it's still 0 for sine. Sine of pi over 2 is 1, but this one gets up to 2. 0, instead of -1, it's down to -2, back to 0. So we'll plot these points. 5, 0 is where we start. We end up here at 0, 2, then -5, 0, 0, -2, and then back to where we began. So apparently it's not in this round, but it's not, well, it kind of looks like Stewie, but it's not perfectly round. It's not a perfect circle. We will talk about these creatures soon enough, but if you know the word, then you can use it now. So this one, we are going counterclockwise around an ellipse. And then we're starting at the point 5, 0. In this case, we're making one complete loop. So it might be kind of interesting to do this one on the calculator, and we'll see it trace out an ellipse for the first time this semester. Okay, so what are we doing here? 5 cosine of t, and the next one is 2 sine of t. Okay, and then the window, let's see, so 0 to 2 pi is the window that they're given. Let's do 0.1s, and we can change that if we want. So -6 to 6 is fine if we want it to look like graph paper that we have. Okay, so let's graph this. We're expecting it to start here, go counterclockwise, and then wrap around and then stop. Okay, that looks pretty good. K, all right, I don't know what's going on with K. It's got different graph paper from the others. Let's give it a shot. X is ln of t and y is t squared. So 1 to 5. All right, let's go ahead and make our table. I don't know exactly where to put the table. Put it over here. So t, x, and y. Okay, so 1 to 5. 1, 2, 3, 4, and 5 for t. And then we're going to plug these guys in. All right, so let's do the t squared part first because that's easier. So we're just squaring these guys for the y's. So 1, 4, 9, 16, 25. And then we need to do ln of these guys for the x's. All right, so ln of 1 is easy. That's 0. But the other guys, I'm going to need some help from the calculator. So let's try this. Okay, so we're doing ln of a bunch of numbers. So ln of 1, ln of 2, ln of 3, ln of 4, and then finally ln of 5. Okay, so those are the numbers that we need. So we'll just round it to the nearest tenth. 0.7, 1.1, 1.4, 1.6. Okay, let's plot these points on our grid. Okay, so the first point is 0, 1. That's there. Next one, 0.7, 4. So 0.7 and then up to the 4 line, which is here. And then 1.1 and 9. 1.1, 9, I think that's here. 1.4 and 16. And finally 1.6, 25. 1.6 and then 25 there. So I was thinking it was going to be straight-ish, but that doesn't look straight anymore. Beginning part looked kind of straight, but it looks like it's curving up more and more rapidly. So let's see if we can figure out exactly what this is, what this equation is in more familiar terms. So let's eliminate the parameter. So here we're going to solve for t. So hit both sides with an e, or just use the definition of what x equals ln of t means. It means e to the x is t. And then we're going to plug that into the other equation. So y is equal to t squared, which is really e to the x squared, or e to the 2x. Oh, so apparently this is an exponential growth function. Does that seem reasonable looking at the graph? Oh yeah, now it does. I recognize this. So we're going that way. And yeah, and so we're following this curve up and to the right. And it's hard for me to know exactly what's happening with the speed. It's definitely not constant because this is a big distance here compared to this distance. But that distance doesn't look too different from this distance, which doesn't look too different from this distance. But I think if we had a few more points, we might get a better sense of what was happening. But I guess we can say definitely that this is following an exponential growth. And we're starting at the point, what, 0, 1? So the speed isn't constant. You know what, I want to know a little bit more about the speed. Can we do 2 more points here? 6 and 7. Okay, so if we plug 6 in and square it, we'll get 36, and then 7 squared is 49. And let's do just a couple more of these ln's here. So ln 6 and ln 7. So 1.8, 1.9. Okay, so what's going on here? So it's hard because we run out of graph paper, but we move a tiny bit to the right and then way up to 36, and then a tiny bit more to the right and way up to 49. So it feels like we're hardly moving at all to the right. Then we're moving up more and more. Yeah, I don't really know. I was hoping it would be clear that we were like either drastically speeding up or drastically slowing down, but it's not clear to me. Let's use the calculator to help us out a little bit. Okay, so we're going to graph these two, ln of t and t squared. Okay, the window. Let's see. So we went from 1 to 5, but how about we go like from 1 to 10 maybe? T step of 0.1, okay, that's fine. The min is 0. The max doesn't really need to be too big at all. Let's go up to 3. And then for the y's, 10 squared is 100, so let's go like to 120 at tens. So let's see what it does. I don't know. Want to see it again? So it was definitely quick in the beginning and then slower. Is it still slowing down as we get up to there? I'm not sure. Let's go a little bit further. How about we go to 20? And then 20 squared is up at 400. So let's get past that number. Yeah. Looks like it's slowing down. Yeah, so sometimes it's not so easy to know exactly what the behavior is. Okay, next page is the learning objectives. So homework is in the usual place. Again, don't forget project and required form. You should be working on those things, and the quiz is coming up next class.